Assalamualaikum warahmatullahi wabarakatuh. This is part 2 of welding. Fusion is one of the methods to achieve the coalescence in welding. So in order to accomplish the fusion, a source of high density heat energy must be supplied to the weighing surface so that that temperature will cause localized melting of the base metal or the filler metal if the filler metal is used. So for metallurgical reason, it is desirable to melt the metal with minimum energy but high heat densities. Power density can be defined as the power transferred to the work per unit surface area. So, in terms of the power density, if the power density is too low, the heat will be conducted into the workpiece instead of melting. So that melting will never occur. So if power density is too high, localized temperature will vaporize the metal in the affected region. So there is a practical range of value for heat density within which melting can be performed. If comparison is made between the welding process, oxy-gas welding, oxy-fuel gas welding develop large amount of heat during the process, but heat density is relatively low because the heat will spread to the area environment more than to the workpiece. So oxyacetylene gas, which is the hottest oxyacetylene used in the oxy-fuel gas welding, burn at a top temperature around 3500 degrees Celsius. So for arc welding, it will produce high energy over a small area, resulting in local temperature around 5500 degrees Celsius to 6600 degrees Celsius. So as for comparison, in the table you will see for oxy-fuel gas welding, it will be around 10 watt per mm squared estimation of the power density. For arc, it will be around 50 watt per mm squared. Resistant welding, it will be 1000, laser beam 9000, and electron beam is 10,000. So power density is a power entering surface divided by the corresponding surface area. So power density can be calculated by using PD equal to P over A. So PD is the power density, which is watt per mm squared. So P is the power entering the surface, and A is the surface area over which energy is entering. So let us see the example for power density. A heat source transfer 3000 watt to the surface of a metal part. So the heat impinges the surface in a circular area with intensity varying inside the circle. The distribution is as follows: 70% of power is transferred within a circle of diameter equal to 5 mm, and 90% is transferred within a concentric circle in a diameter of 12 mm. What are the power density in A, the 5 mm diameter inner circle, and B is the 12 mm diameter ring that lies around the inner circle? So if you want to illustrate it so that you can understand, so for example, this two circle. Okay, so the first one is 5 mm and this one is 12 mm. Okay, so for the first one, the power is supplied to this 5 mm diameter area, and after that is the 12 mm power area. Okay, so let's see the A first. The inner circle has an area because this is 5, so then you can calculate the area. A equal to pi d squared over 4, so that you get the first area is, this one is 19.63 mm squared. So the power inside this area P is distribution is around 70%, so 0.7 times the 3000, which is the power. Okay, so that you will get 2100 watt. Okay, so thus the power density will be 2100 divided by the area, which is 19.63 mm squared, so you get around 107 watt per mm squared. Now for B, the area of the ring outside the inner circle, so this area, this circle, this area, so what you have to do is first calculate the area, which is A 12 squared minus 5. Okay, so because we want this area, so you have to do minus this area first. Okay, so then you will get the area is 93.4 mm squared. So for this region, only 0.9 is distribution, right? So now 0.9 times 3000, but we have to minus with 2100. Why? From this 3000, 2100 already absorbed by this area. Okay, so then 0.9 times 3000 minus 2100, so then you will get 600 watt. So 600 watt divided by 93.4, so you will get 6.4 watt per mm squared. Now, let's see the unit energy for melting. So what is a unit energy for melting? It is a quantity of heat required to melt a unit volume of the metal. So this one is represented as UM. So UM is the sum of heat to raise the temperature of solid metal to melt to melting point. So this one is depending on the metal volumetric specific heat, and then heat to transform metal from solid to liquid phase at melting point. So this one also depend on the metal's heat of fusion. So unit energy can be calculated by using this equation. UM equal to KTM squared. Okay, so UM is the unit energy for melting, which is joule per mm cube. Tm is the melting point of the metal on the absolute temperature scale. Okay, and K is the constant whose value is 3.33 times 10 of power negative 6 when the Kelvin scale is used. Okay, so and K equal to 1.467 times 10 power of negative 5 for Rankine temperature scale. So before we can do any calculation, we have to understand the heat transfer mechanism in welding. So not all the input energy is used to melt the weld metal. So there are heat transfer efficiency, F1, which is the actual heat received by the workpiece divided by the total heat generated at the source. And then we have also melting efficiency, which is F2. Is a proportion of the heat received at work surface used for melting. So the rest is conducted in work metal. Let's see the heat transfer mechanism in welding in this picture. Okay, so for example here, you will see that this is the heat source of the welding. Okay, so when we perform the welding process, there will be F1, which is the heat transfer to the work surface. Okay, so then there will be also heat losses. So this one is 1 minus F1. So this is the amount that heat transfer to the work surface. The balance will be heat losses to the environment. And then we also have F2, where the heat used for the melting the base. And then there will be 1 minus F2, which is the heat dissipated into the workpiece here, that not for the melting. So based on this one, there will be heat available for welding can be calculated by using HW equal to F1 times F2 times H. Okay, so HW is the net heat available for the welding. So F1 is heat transfer efficiency, F2 melting efficiency, and H is the total heat generated by the welding process. So then you will get the final HW by using this calculation. Heat transfer efficiency F1 is a proportion of heat received at work surface relative to the total heat generated by the source. So this one is depending on the welding process. For example, oxyfuel gas welding process are relatively inefficient, and arc welding process are relatively efficient. So which means for F1 for the oxyfuel will be less than the arc welding F1. Melting efficiency F2 is a proportion of heat received at work surface used for the melting, where the rest of the heat will be conducted to the work. So this one is depend on the welding process, but also thermal properties of the metal, and also joint shape, and also work thickness. So if the metal is high in thermal conductivity, for example aluminium and copper, so instead of the heat used for melting the material, more heat will rapidly dissipate into the other part. Energy balance equation is the net heat energy into welding operation equal heat energy required to melt the volume of metal welded. So this equation is become HW equal to UMV. So where HW is the net heat energy delivered to operation, UM is the unit energy required to melt the metal, and V is the volume of the metal melted. Most welding operations are rate processes instead of just a process of the heat itself. So that is the net heat energy is delivered in a given rate. So the weld bit is made in a certain travel velocity. So this characteristic, for example, of most arc welding, many oxyfuel gas welding operation, and even some resistant welding operation. So therefore it is appropriate if we want to express the equation of the rate balance equation. For example, RHW equal to UM RWV. So RHW is the rate of heat energy delivered to the operation for welding. RWV is the volume rate of metal welded, and in welding of a continuous bit, the volume rate of metal welded is the product of weld area AW and travel velocity V. So since in the continuous bit, the volume rate of metal welded is the weld area and travel travel velocity. So if we want to substitute it into the equation, it will become RHW equal to F1 F2 RH equal to UM AWV. So that you can calculate the value based on this equation. So here is the summary of the equation that we already see previously. For example, the power density equal to PD equal to P over A, unit energy UM equal to KTM squared, heat available for welding HW equal to F1 F2H, energy balance equation HW equal to UMV equal to F1 F2H, and energy rate balance equation can be written as RHW equal to UMRWV, and RHW can be written as equal to F1 F2 RH equal to UMAWV. This one is for continuous bit. So now let us see an example. So the power developed in arc welding operation equal to 3000 watt. This is transferred to the work surface with heat transfer factor equal to 0.8. The metal to be welded is aluminium whose melting point is given in table 25.2. So there's in the next slide as so it is given 930 Kelvin. Okay, assume the melting factor equal to 0.4. a fillet weld is to be made with a cross-sectional area equal to 20 mm squared. So determine the travel speed at which the melting operation can be accomplished. So the first thing that we want to see is determine they want the travel speed at which the welding operation can be accomplished. First of all, you have to detect what is the equation that you can use um, to calculate this one. If you can see to the summary of the equation, so RHW equal to F1 F2 RH, or you can also equal that UMAW, right? So if we put that UMA V equal to F1 F2 RH, then if we arrange the equation, you will get this equation. Okay, so V equal to F1 F2 RH over UMAW. So now F1 we already have, F2 we already have, RH also you already have. So what you have to calculate now is the because we don't have the yet. AW is already given, right? So what you have to do is now equal to KTM squared, right? So K is 3.33 times 10 power of negative 6 times the K. Okay, the temperature, the temperature squared, right? So temperature in Kelvin. So temperature in Kelvin is 930 K. So 930 squared, so that you will get the value 2.88 joule per mm cube. So now when you substitute the value inside the equation here, F1, F2, and then the RH, and then divide by UMA, right? UM and then A. So you will get the velocity equal to 16.7 mm per second. Now you can try to solve it yourself. So as for A, the solution is given. So try to solve the B. How will it look like? So you can use this table for the melting temperature for the material. So as we see in the example previously, aluminium alloy is 930 K. Okay, if in the Rankine is 1680. Some features of the fusion welded joint are typically contain of fusion zone, weld interface, heat affected zone, has and unaffected base metal zone. Typical fusion welded joint can be presented in picture A and B. So cross section of a typical fusion welded joint. So A is the principal zone in the joint. So if you perform the welding, so you will see that this is the fusion area where the welding take place. Okay, so then there will be one layer here, what we call as weld interface, and then there will be another area over here, what we call as heat affected zone or HAZ, and the other area is the unaffected base metal. Okay, so in terms of the grain structure, if you can see, there will be a columnar grain in the fusion zone, and then there will be coarse grain in the HAZ near the weld interface, and fine grain in HAZ away from the weld interface. So the original cold work grain will look like this one, and this one will become fine grain in HAZ away from the weld interface, and the coarse grain in the HAZ area. So what is heat affected zone? Let us see what is a heat affected zone. So metal that has experienced temperature below melting point but high enough to cause microstructural changes in the solid metal. So this is what we call as heat affected zone. So chemical composition same as the base metal, but this region has been affected by heat that come from the welding process, so that these properties and structure has been altered. So effect of the mechanical properties in the HAZ area is usually negative, So in this area, usually welding failure will often occur. So here are the example where the heat affected zone is very big and showing here. So this is the heat affected zone. So in here also you will see this like burning area over here. If we cut and see into the cross section of the work part, okay, workpiece, you will see this is the fusion zone. Okay, so this is where the melting happen, and this is the heat affected zone. You can see the difference of the microstructure compared to the area that is not affected. Okay, that's the end for the welding part 2. See you in part 3.